In current day society, we as humans are more connected than ever. It's very common that we live outside of the cities that we work in. Friends and family that are miles away are separated by mere train rides. And long-distance relationships are no longer doomed to fail purely because of travel time. In other words, our big world is getting smaller and smaller with the increase in connectivity. But as our world is getting smaller, our problems are getting bigger. Because with the increase in connectivity also comes the increase in demand for fast transportation. Now, this trend is not new, and it is estimated that by the year 2050, the demand for transportation will have increased with 100%. It's in the nature of people to want to go further and to want to get there faster. Dear partners, family, friends, alumni, and of course, my dear, dear team. I would like to welcome you tonight in this incredible location in the Nieuwe Kerk in the city center of Delft to the design reveal of Delft Hyperloop 9. Tonight, we're going to tell the story of hard work that results in an incredible Hyperloop design. I am Sophie Loogman, and I am the proud team captain of Delft Hyperloop 9. As a team captain, I'm honored to lead the team towards reaching its extraordinary and soon to see extremely ambitious goals that we have set for ourselves. It is my role to provide a collaborative working environment that fosters innovation and collaboration. Together with the project manager, Douwe Vos, and the chief engineer, Daniel Both, we form the management of Delft Hyperloop 9. Together, we are responsible for the overarching strategy that allows the team to reach its full potential. And tonight, we have the privilege to share with you the story of Delft Hyperloop 9. A story which is long from finished. However, it's already filled with incredible accomplishments and milestones. Tonight, we will tell the story of hard work that comes together in an incredible Hyperloop design. And the story of Delft Hyperloop originates in the problem of climate change. Now, this problem is also not new. With the invention of the steam engine in the early 18th century, a kickstart was given to the Industrial Revolution. And this was the beginning of a series of rapid innovations and developments that led to the world that we know today. However, the dream of a world with endless resources was scattered early in the 1900s. And in 1972, the first ever global climate summit took place in Sweden. Now, one question that arises after this history of recognition is, why haven't we found a globally accepted way of sustainable transportation yet? Why is it that the smartest people of our society have not been able to transform the way we move into one that is non-destructive to our planet? Now, the answer to that question can be found in one very simple example: the bike. Now, this may seem like a silly example because it appears very obvious that the bike is not the solution to our transportation issue. However, when we zoom in on the bike, we can define what is needed to find a way of travel that can, in fact, be the solution to our overly full and polluting transportation network. And we're going to do this by using an example. Let's say we're going on a trip together. Let's say we're going to Paris. It's a lovely city, only 500 kilometers away, and we decide to go there by bike. A terrible option, we know that, but let's investigate why it is such a terrible option. Now, the first and most obvious reason that it's such a terrible option, it is that it would take us an astonishing 30 hours to get to Paris. So, long travel time, or speed, is the first indicator that a sustainable mode of transport is going to be unsuccessful. On top of that, even if we had the time to bike all the way to Paris, we would get tired. And it might rain on our way over there. And altogether, it's just extremely inconvenient. So that is the second requirement that we have for transportation. It needs to be convenient and comfortable. On top of that, the bike is quite cost effective because we don't need any fuel. So besides sustainability, we have the criteria of speed, convenience, and cost that determine whether a sustainable mode of transportation is or is not going to be used. And when we use these 4 criteria, we can see why we have not found a suitable, sustainable way of transport yet. Because we use the same example of going from Delft to Paris with more obvious forms of transportation. Say, we take the car. Now, it's deemed a lot more convenient than biking all the way to Paris. However, we do need fuel, which is polluting and expensive. So it's not ideal. Another way to go to Paris is to fly there from Schiphol. Now, if you look at the numbers of the aircraft industry, we know that it's considerably more polluting. But it does score high on speed because it only takes us 1 hour to get to Paris. Lastly, we then have also the high-speed train, which is a more sustainable option. But when we compare ticket prices, we see that often the ticket prices of the high-speed train are higher than those of its polluting siblings. So in conclusion, the choice of transportation is a constant trade-off between the criteria of sustainability, speed, cost, and convenience, because none of the existing travel methods can effectively address all of them. And this trade-off is encountered by every segment of society on a daily basis. It is encountered by produce companies when they decide how they want to deliver their goods. It is encountered by governmental institutions when they decide what infrastructure to invest in. And it was encountered by everyone here in this room today when they arranged their journey to the Nieuwe Kerk. And while sustainability is more important than ever, it remains only one of 4 criteria. And that is why investments in new methods of travel, in new innovative infrastructure, and in new logistical setups are unavoidable. To ensure a future in which we can stay connected, we need to stop compromising. And at Delft Hyperloop, we believe in such future. We believe in a future in which we are connected without compromising. We believe in a world in which sustainability, speed, cost, and convenience meet. And it is our commitment to develop a way of travel that allows the world to stay connected while connecting sustainably. And that is where the Hyperloop system comes in, a new method of travel. It successfully addresses the 4 dominant criteria of transportation. It makes use of the advantages of the known travel methodologies while mitigating their drawbacks. Now, the Hyperloop system differentiates itself in 2 dominant ways. Firstly, we make use of magnetic levitation. So by magnetically levitating ourselves off the ground, it is established so that there's no contact surface with the surrounding infrastructure whatsoever. And this means that the rolling resistance that you experience in a car or train, for example, is no longer applied to the vehicle. Secondly, the Hyperloop vehicle is then placed in a near vacuum environment. Now, this means that all the air is sucked out of the tube that is surrounding the Hyperloop vehicle, and thus also air resistance can be neglected. Now, by minimizing these forces of friction in a low pressure environment, the result is an incredibly energy efficient system. And this system can reach speeds of up to 1,000 kilometers an hour. So we see that already in the factors of sustainability and speed, the Hyperloop outperforms all of the existing travel methods. But as I said, at Delft Hyperloop, we don't compromise. So the Hyperloop system also needs to be cost effective. Now, one big advantage about the Hyperloop system is that it needs very little to no maintenance and operational costs. Because there's no contact surface with the infrastructure, the maintenance cost can stay very low. And because it's an autonomous system, there's no human operation needed. Lastly, we ensure the convenience of the Hyperloop system by integrating its stations with already existing travel hubs. Engineers from Delft Hyperloop 8 last year showed that a Hyperloop station can integrate seamlessly with Schiphol Airport. And this allows intercontinental travelers to conveniently exit their flights and continue their journey on land with a Hyperloop system. And if we then look at our trade-off of the trip that we were taking to Paris, we see that the Hyperloop system is a clear winner. It successfully addresses the 4 key pillars of transportation, making it a game changer for global mobility. Now, where do we envision the Hyperloop system maximizing its potential? As the Hyperloop system goes at more than 1,000 kilometers an hour, it is not effective to be used for short distance travel. The Hyperloop is most efficient at distances from 500 to 1,500 kilometers. And this is exactly the distance that a lot of short-haul flights travel. And the thing with short-haul flights is that because of their relatively high takeoff distance, they are a big reason as to why air traffic is such a big polluter. And that is also exactly where we see the Hyperloop contributing to a sustainable transportation network. So, at Delft Hyperloop, it is our vision to accelerate the implementation of a full-scale Hyperloop system, offering a sustainable and time-efficient alternative to short-haul flights for connecting major cities. Tonight, we came together in a place of history to look at a future. A future which requires collaboration and integration. And that is also why we decided to come together here in Nieuwe Kerk in Delft. Because where pioneers in Delft have always led us towards radical innovations, the church has been leading towards cohesion. It's a place where people come together in unity and community. It's a place where believers come together. So I invite you to believe. Believe in a world with a Hyperloop system. And also know that you're not alone. Advocating politicians, engineers, and specialists went before you. So let's see how they came together.
Mijn naam is Daniel Kofman. Ik werk dit jaar alweer 25 jaar bij Siemens. En ben sinds 2 jaar verantwoordelijk voor samenwerking met het onderwijs en studenten en ook studententeams zoals Delft Hyperloop. Het eerste systeem, daar staat nog heel veel technologie in de baan. Doordat ze van het project geleerd hebben en ook de nadelen van het project geleerd hebben, dat ze nu tot een ander concept gekomen zijn waar alle intelligentie in de pot zit. En die baan dus eigenlijk dom geworden is.
Door in het voertuig te zetten ben je natuurlijk toch wat onafhankelijker van de buitenwereld. Want de baan heeft alleen maar stationaire systemen. Hè? Dus de trein kan toch blijven rijden, ook bij stroomuitval. Jullie hebben batterijen in de trein gezet. Dat is een belangrijke wijziging in het systeem. Waardoor het nog veiliger is.
Dus ook heel erg goedkoop. Dus die infrastructuur is veel makkelijker aan te leggen nu. En dat is wel een flinke stap naar de haalbaarheid van een Delft Hyperloop. Niet een Delft Hyperloop, maar van een Hyperloop in het algemeen.
De Hyperloop is voor mij een heel mooi, nieuw, innovatief mobiliteitsconcept. Wat ons kan helpen om mobiliteit echt te verduurzamen. En veel mensen realiseren zich niet dat een heel groot deel van onze CO2-footprint in internationaal reizen zit. En dat is nou juist iets waar de Hyperloop een hele mooie oplossing voor kan bieden. Ik herinner me nog goed dat het allereerste Delft Hyperloop team de wedstrijd won. En ja, wat dan ook heel leuk is om te zien dat uit zo'n wedstrijd eigenlijk een hele nieuwe industrie ontstaat. Een aantal van de jongens uit dat eerste team toch een bedrijf zijn begonnen, Hyperloop. En nu ook binnen Europa echt wel de aanjager zijn, eigenlijk wereldwijd ook wel, de aanjager zijn van de ontwikkeling van Hyperloop-technologie.
Ik ben Tim en een van de oprichters van Hyperloop en daarvoor ook van Delft Hyperloop. Als je kijkt is reis natuurlijk iets heel menselijk wat we al sinds het bestaan van de mensheid doen. Eerst met paard en wagen, dan je auto's, treinen, vervolgens vliegtuigen. Maar voor de laatste decennia, zelfs eeuwen, gebruiken we gewoon die transportsystemen. Terwijl we wel zien dat alles eigenlijk nagenoeg vol zit of niet duurzaam is. En de groei van mobiliteit die is ook verwacht te verdubbelen tot aan 2050. Terwijl we vandaag de dag al met een heel vol systeem zitten. Dus hoe gaan we dat oplossen? En dat is wel iets waar de Hyperloop echt het verschil kan maken.
Ik zie het niet zo snel gebeuren dat we het treinsysteem in Europa goed op elkaar aangesloten krijgen. Het is gewoon ongelooflijk lastig om in een bestaand systeem veranderingen aan te brengen en daar interoperabiliteit te realiseren.
Hyperloop is helemaal nieuw, dus je kunt van vooraf aan beginnen. Het is niet per definitie de NS die je zou moeten rijden. Je kunt de baan privaat-publiek aanleggen. Je kunt het erop rijden aanbesteden aan private partijen. En dat maakt dat je veel meer kans hebt om zo'n systeem. Dan ben je onafhankelijk van de rest.
Dus een heel nieuw systeem van scratch af aan bedenken geeft je de mogelijkheid om dat meteen in één keer interoperabel te maken, waarbij alle verschillende operators gebruik kunnen maken van het systeem en daar een heel mooi Europees concept van te maken.
Ik zei vroeger al, als er geen weerstand is, weet je zeker dat je geen innovatie belandt. Dus hoe meer weerstand je krijgt in de samenleving, hoe meer dat je weet dat het een echte innovatie is. Het lastige aan innovatie is tijdstip. Sommige innovaties komen te vroeg. Een innovatie die te laat is geen innovatie meer. Want dan is die er al. Timing is zo ongelooflijk belangrijk. Wij waren met onze Trans Rapid gewoon een beetje vroeg. Nu is het goede moment.
At Delft Hyperloop, we advocate for the implementation of a full-scale Hyperloop network. However, we reckon that challenges are to be overcome before this implementation can move into reality. And as Martin already said in the video, humans are inherently resistant to change. New ideas and new concepts have always experienced resistance and pushback by society. And skepticism and opposition are no exception when it comes to new ideas. Take the Wright brothers, for example, who built the first aircraft. At Delft Hyperloop, we aim to learn from those changemakers that came before us. We focus and familiarize the people with the Hyperloop technology simultaneously to its technological development. Behind me is the Hyperloop experience, which was exhibited in the Nieuwe Kerk over the past 10 days. We want to take the public along on our journey towards the realization of a Hyperloop system. But to make this Hyperloop system a reality, one of the leading technical challenges in the industry is standardization. Because the Hyperloop is most efficient at distances from 500 to 1500 kilometers. And if we then look at the implementation of a Hyperloop network in Europe, we see that this involves crossing multiple borders. A unified approach on what is the best Hyperloop technology is needed to make this a reality. And this poses a significant challenge in terms of international cooperation and regulation. Unity and agreement across borders is required. However, this standardization is not that far from reality. In Veendam, in Groningen, the first Hyperloop test track of over 400 meters was completed last year. And this track, located at the European Hyperloop Center, was funded by the Dutch government and the European Union. And it is the first version of what is expected to move towards a standardized European Hyperloop network. A first pilot line is expected by the year 2035 of multiple kilometers. Now, as at Delft Hyperloop, it is our vision to work towards the accelerated implementation of a Hyperloop network What better way than to contribute to one of its leading technical challenges, standardization. That's why I'm proud to announce the goal of Delft Hyperloop 9. Because our goal is to be the first student team that will demonstrate a fully upskilled Hyperloop system in the European Hyperloop Center. And we're going to demonstrate this system during the European Hyperloop Week in July. The European Hyperloop Week is a competition where student teams from all over the world come together and measure their technology against each other. And one can win multiple awards during this competition. And as a team, we aim to win the overall award. Now, this award combines the demonstration, our design, and our research. And ultimately, we plan on winning the entire competition. As Delft Hyperloop 9, we set steps towards this milestone every day. And choosing such goal, such ambitious goal, with 40 students that need to share the same drive is not easy. And Douwe is going to tell you more about how we got to this goal and how in the end we will achieve it.
Thank you, Sophie. After presenting such an ambitious goal, I think it is good to take everybody back to the beginning of our year. On the 18th of August, 30 individual students gathered in front of our dream hall, not knowing what to expect of the time ahead of them. And at the start of this project, the most important thing was to create a bond. And that is what we did on our team weekend in Venlo. But besides creating a bond, there was another important aspect that we had to tackle. And that was to create unity in the team, with the shared mission of where we see ourselves in the innovation of the Hyperloop technology. And this mission had to be embraced by every single team member, because this mission also was our support for motivation this entire year. When we as a team or as a single engineer are in a tough time, this mission would always be something that we could fall back on. And that mission is, as Sophie mentioned, to be the first student team to demonstrate a fully integrated Hyperloop system in the European Hyperloop Center. My name is Douwe Vos, and I'm the project manager of this year's Delft Hyperloop team, which among others means that I oversee the planning and the finances. And to reach this goal we just mentioned, we go through all 5 phases of a design cycle. We go through the phases of concept, design, production, and testing. And every year, we start in the conceptual phase. And this is a phase where we unknowingly already are in our team weekend in Venlo. In this conceptual phase, the most important thing is that we as Delft Hyperloop 9 decide on what we want to achieve that year. And at the end of this conceptual phase, we will only have set a goal. But setting a goal is only a start. It's only an idea. Afterwards, an intensive design period starts. Here, we make all design choices that will be implemented in the future. Every scenario of every subsystem will have to be simulated to make sure we are as well prepared as we can be for when production starts. And this is also the critical point in our project and where we integrate all subsystems into one design. In our main assembly, we combine all our components to make sure they fit and work good next to each other. And as I'm talking here, we stand on the brink of our production phase. The phase where all the brainstorming, designing, and hard choices made will finally come to life. Everything we have worked towards is finally becoming reality. But this, of course, also presents a lot of new challenges. And then finally, the most uncertain part of the project, the testing phase. To make sure our pod delivers what it has to, during the European Hyperloop week, we have a very long testing phase. As every engineer here in the Nieuwe Kerk can testify, something you design and produce will never work the first time. And even better, the second and the third time, it probably will also fail. And that is why we test and fail. We are constantly looking at new solutions and implement them again and again. And for going through this design cycle, we only have 1 year. This is a process companies and projects have multiple years to work upon. But we don't have that luxury. If a subsystem fails, we can't have a delay. Our competition, the European Hyperloop Week, will still start on the 14th of July. So we have to look at alternative solutions or simply just work harder. As we are going to demonstrate in the European Hyperloop Center, scaling up is one of the major challenges that we will face this year. Scaling up is not just about making the pod bigger. It is about rethinking the entire design. A bigger pod means increased weight, higher stresses, more power demands, and new safety concerns. And scaling up doesn't only bring technical challenges. It also tests our daily problem-solving skills. For an example, a pod this heavy, we will still have to move, test, and assemble without any heavy moving equipment. And to do this, we have extreme time constraints. We have less than 12 months to design, produce, and test a fully integrated Hyperloop prototype. And going through this design cycle in 1 year is one of the things that I find so extraordinary of Delft Hyperloop. We are not bound by the limits of traditional projects. We have the freedom to fail and learn from our mistakes. Every single engineer in our team started this year with little to no hands-on experience on a project of this size. The most important skill they brought with them is an eagerness to learn. Our success will not be decided by how knowledgeable a single engineer is. In our team, we still have multiple engineers who haven't even finished their bachelor's yet, while still engaging on the problems that we face day to day. No, our success will be established by how motivated we are, how open we are to learn from our mistakes, and how determined we are to overcome these obstacles that we will face. Because we have already faced many obstacles this year. But if there's one thing that's certain, the rest of our year will only present more. Because Delft Hyperloop is not just an engineering project. Delft Hyperloop is a vision. We are building something that does not exist yet. Every team of Delft Hyperloop for the past 8 years has overcome a problem which had never been solved yet. And from all these alumni, we gain valuable insights and learn from the mistakes they made. But that only gets you so far. As all the alumni who have gathered here in the Nieuwe Kerk can testify, once you commit a year to Delft Hyperloop, there will be a point that there is no one who can help you. There is no textbook, professor, engineer, or promoted doctor who knows the answer to your problems. But still, we always find a way. And that is the strength of Delft Hyperloop. Standing here and talking about all these challenges is one thing, but actually solving them is another. This is why I am proud to introduce you to my team members and their departments, who with their ambition, drive, and passion will overcome all the challenges that we will face this year. May I have a big round of applause for Delft Hyperloop 9. Technical innovation isn't the only thing that we need to do to reach our goal of accelerating the implementation of a Hyperloop system. We as Delft Hyperloop 9 also look at the challenges that we will face in multiple years. This is where our scalability department comes in. The scalability department looks at two sorts of technical challenges, or two sorts of challenges that will arise in multiple years. Technical challenges and socio-economic challenges. Starting off with Alexander and lead scalability Mike, who are our full-scale engineers conducting technical research. A Hyperloop infrastructure won't be able to go straight through diverse landscapes, and that is why it needs to be able to make sharp turns. A critical point in this is banking. Banking means leaning into the turn. And this technique already exists in other systems. And that is why Alexander and Mike are conducting research on which form of banking is the most feasible for the Hyperloop technology. And together with Oscar and Simone, our full-scale engineers conducting socio-economic research, they complete the scalability department. As you can imagine, implementing a whole new infrastructure comes with a lot of problems. High-speed rail has proven that this is very complex and expensive to implement. This is why Oscar and Simone are diving into literature and talking to a lot of experts to learn lessons to create strategies for the future implementation for a Hyperloop network. Then moving on to our business department. The goal of the business department is to familiarize everybody with the concept of Hyperloop and to secure the team with all resources needed to make our pod reality. Our business department is split up in 3 sub-departments: partnerships managers, public relations, and design engineers. Starting off with the partnerships managers, Isa, Rijk, and Okke. Isa, Rijk, and Okke are responsible for maintaining contact with all current and prospective partners of Delft Hyperloop. And by doing this, they make sure that we are able to make our pod this year. Because partners, nothing we do would be possible without you. So thank you. It's because of you that we have the opportunity to work on this project for the year. And then the public relations department, containing Lara and Zoe. Lara and Zoe are responsible for familiarizing the public with the concept of Hyperloop. And they do this by creating PR strategies, and organizing all the events, like the lovely one we are at right now. And last but not least, the design engineers, Cas, Floris, and Yannick. Cas, Floris, and Yannick take Hyperloop a step closer to reality by making visualization that is both informative and aesthetically pleasing. This year, their focus lies on the implementation of cargo in a Hyperloop network, and they took it a step further. They are also conducting research in the viability of a pilot cargo line. And then our 5 tech departments, starting off with the backbone of our pod, the mechanical department, consisting of lead mechanical Roman, David, Bernard, Vic, Reiner, and Medange. The mechanical department is responsible for all the fundamental components in our pod, like the aeroshell, the chassis, the emergency brakes, and the vacuum box. Furthermore, they are also responsible for making our very own replica test track of the European Hyperloop Center, where we will do all our tests on in front of the Dream Hall. Moving on to the levitation department. As you all should know, Hyperloop levitates. And our levitation department executes hybrid electromagnetic levitation. This ensures, while operation, our pod is never in any contact with the track. Our levitation department consists of lead levitation Bram, Koen, Wouter, Radek, and Siddharth. And because we don't make contact with the track, a conventional motor does not work. This is where our propulsion department comes in, containing lead propulsion Filipina and engineers Quint and Ruben. They are responsible for making our very own efficient propulsing motor, based on magnetic principles. As you all can imagine, all these different subsystems have to communicate with each other and exchange data. This is one of the many things our Sense and Control department takes care of. Lead Sense and Control Pablo and engineers Jorian, Thijs, Dinu, Harry and Alexander also make sure different sensors gather critical data to ensure the safe and efficient operation of our pod. And last of all these departments wouldn't work without power. This is why we have our powertrain department, consisting of lead powertrain Sam, Dirk-Jan, Niels, Sam, Lars, and Leon. Furthermore, they are also responsible for creating our very own custom-made motor drives, which power our motor. Talking about all these subsystems, they will never work individually. The only way that we will make our pod reality is by combining them all into one design and eventually one realistic pod. And it is my pleasure to announce the one that is responsible for the integration of all our components. Our chief engineer, Daniel Bolt.
Thank you, Douwe. And good evening, everyone. My name is Daniel Bolt, and I have the honor to be the Chief Engineer of Delft Hyperloop 9. This year, our team has set out to achieve something truly groundbreaking, creating the largest, fully integrated, student-built Hyperloop prototype and demonstrating it at the European Hyperloop Center in Groningen. As Chief Engineer, my responsibility is to ensure that all technical subsystems integrate seamlessly and function in unity to create a fully operational Hyperloop system. Over the past months, our team has spent a vast amount of time and effort into designing a pod that's not only scalable, but also safe, reliable, and ready for the future. Before we delve into the details of our design, let's talk about design philosophies. At Delft Hyperloop, every decision we make is guided by our core principles and design philosophies: innovation, scalability, and reliability. This makes sure that our work contributes to a system that is viable on a large scale. We have always been a team that has been driven by ambition. We are here to push the limits. However, being on the front lines of development isn't easy. It requires navigating the unknown, encountering setbacks, and learning from our mistakes. This requires meticulous engineering, rigorous testing, and learning from our mistakes. We achieve this through extensive simulations, iterative prototyping, and pushing components to their limits, and sometimes even beyond, to get a better understanding of the consequences of a faulty component. Innovation and scalability are meaningless if the system doesn't work. Our pod is not just a concept. It's a real physical machine that needs to operate under extreme conditions, such as a near vacuum environment. However, innovation doesn't happen in isolation. It is built upon the progress of those who came before us. If you look back to the early years of Delft Hyperloop, there was a focus on reaching high velocities. For example, building a small prototype that was capable of reaching speeds in excess of 350 kilometers an hour. If you now look back to 4 years ago, DHL5 made a critical step in the legacy of Delft Hyperloop. Their design focused more on scalability and stability of the system and less on reaching high velocities. The year after, DH06, with their pod, Helios 1, switched from a track that was underground to a hanging one, where the pod is magnetically suspended from above. This resulted in a more stable system, and it has set the ground for a lane switch. The year after, DH07 achieved full levitation. Now the pod not only levitates in the vertical direction, but also in the lateral direction. Besides achieving full levitation, a new motor was designed, the linear flux switching permanent magnet motor. This resulted in a motor that has much higher efficiencies at high velocities. Last year, Delft Hyperloop 8, with their pod, Helios 3, achieved a major milestone: the world's first scalable lane switch. This groundbreaking achievement has set the stage for the entire Hyperloop industry. For a Hyperloop network to become reality, a pod must be able to change lanes at high velocities without the need for any moving components in both the infrastructure or the pod itself. Building upon the legacy of our predecessors, I'm thrilled to share our journey, how we, as Delft Hyperloop 9, came to our most ambitious design yet. This is the result of 6 months of relentless dedication into designing a pod that pushes the boundaries of what is possible in high-speed transportation and bringing the Hyperloop concept into reality. We are Delft Hyperloop 9, taking a step into reality.
Change. It doesn't take place in coexistence with comfort. A truth very well known in the pioneering city of Delft. Big ideas don't come to life by following the familiar path. They require bold steps into the unknown. The growing demand for transportation is a continuous reminder why Delft Hyperloop was founded. To build a sustainable and fast travel method that will transform the transportation sector as we know it. For this change to be realized, engagement of the world is required. We need to come together and let the innovations guide us. So when this technology is ready for the world will be ready for the Hyperloop. On the shoulders of years of innovative accomplishments, Delft Hyperloop is taking a bold step forward. Our team has set the mission to develop an innovative Hyperloop system that will accelerate the implementation of a full-scale Hyperloop network. We are continuously navigating on the fragile line that separates dreams from reality. Together, we go from vision to velocity. We are Delft Hyperloop 9. And tonight, we're going to take a step into reality. This is THEIA.
with that video, I'm proud to announce THEIA, the largest, most powerful, most technologically advanced pod ever designed by Delft Hyperloop. Many years ago, the planet THEIA collided with Earth, creating the world as we know it today. At Delft Hyperloop, we want to contribute to its preservation by creating a high-speed mode of transport, one that is sustainable, efficient, and ready for the future. THEIA is also the mother of Helios, the sun, making our pod a symbol of scaling up. Where Helios was the first step, THEIA takes it further, stronger, better, and more ambitious. This isn't just a new pod. It's the next step towards a more efficient and cleaner future. THEIA has dimensions and weight which are similar to that of a Volkswagen Golf. However, despite this weight, we are still capable of reaching speeds in excess of 50 kilometers an hour in just 50 meters. The result is a peak acceleration of 3 meters per second squared. This is more than double the acceleration of a modern NS Sprinter train. This is possible due to the peak output power of 150 kilowatts, more than most high-performance motorcycles. Now, let's take a closer look at the subsystems to get a better understanding of how they function. The chassis is the skeleton onto which all of the components are mounted. Therefore, it also needs to be designed and produced first. And I'm proud that as we speak, the chassis is already finished and here at the Kerk in the exhibition. Feel free to take a look after the presentation to get a sense of its scale and witness the next chapter in Delft Hyperloop's legacy. This hybrid space frame is constructed completely from aluminum. This is because the chassis needs to be both incredibly light while still maintaining structural integrity, even with heavy loads induced by both propulsion and levitation. Another important requirement of the chassis is accessibility. All critical components need to be accessible in minimal time during testing. This is something that can become complex, navigating between such a large structure weighing over 125 kilograms. While the chassis is designed for keeping key subsystems accessible, not every component is fit for the harsh environment that a near vacuum is. That's where the vacuum box comes in. Just like the organs in a human body need protection, all critical components, such as electronics, must also be safeguarded from the near vacuum environment to ensure they always function reliably. Right now, it protects all the electronics, but in the future, it will protect you as a passenger. During testing, we prioritize accessibility to enable rapid prototyping. That's why we have placed the vacuum box underneath the chassis, allowing engineers to always have quick access. Furthermore, we have introduced a vertical mounting plate, removing the need for the complex drawer system that was used in previous years, even further streamlining the component access process. And when the time comes to test in a vacuum, we simply put on our curved lids and we are ready for operation in a near vacuum environment. One of the key subsystems of a Hyperloop system is levitation. For vertical levitation, we use a system we call HEMS, Hybrid Electromagnetic Suspension. The hybrid comes from the fact that we use a permanent magnet in combination with an electromagnet. This electromagnet already holds the bulk of the pod's weight, dramatically decreasing power consumption. Now, let's take a closer look and see how the HEMS functions. By placing neodymium magnets on top of a steel laminated U-core, we can efficiently guide the magnetic field that is produced by these permanent magnets in the exact way we want it. If we now suspend the pod underneath the track, the pod will naturally hang at a certain distance. The distance between the magnet and the track is what we call the air gap, which is 13 millimeters, or roughly the size of your index finger. As you can imagine, we want to be able to have precise control over this air gap at all times. And to do this, we place coils around the U-core, and depending on the direction of the current flowing through these coils, we can adjust the air gap against any disturbances the pod may face. However, these coils are of little use if we do not know our air gap in all directions at all times. To measure this air gap, we use laser offset sensors. These sensors work by emitting a laser beam onto the track, and from the reflection, we can calculate the distance between the pod and the track. The result is that we measure this distance 9,000 times per second for each of our 16 laser offset sensors. For lateral levitation, we use a system very similar to the HEMS. However, this time we do not use a permanent magnet. This is because we are not working against gravity in this direction, and we only want the EMS to generate a force if you are not perfectly centered in the track. By combining the HEMS and EMS systems, we can actually achieve full levitation of our 1400 kilogram pod while using less energy than a vacuum cleaner. The second key defining aspect of a Hyperloop system is magnetic propulsion. Reaching high velocities without any physical contact with the infrastructure is a major challenge. To overcome this challenge of reaching high velocities in the European Hyperloop Center, we have designed a brand new motor. A double-sided P8 S24 linear synchronous reluctance motor. A mouthful. So for now, let's call it our motor. Our motor works by precisely controlling a series of electromagnets in a synchronous manner. Instead of simply turning on and off magnets, our motor creates a smooth, continuously shifting magnetic field using a carefully timed three-phase alternating current signal. Now, through careful simulations, we can optimize the geometry of our motor. The result is that there will always be an electromagnet that wants to attract itself in the direction of travel. Now we just need to know what coils need to get what amount of current at any given time. To do this, we need motor drives. These motor drives can control the applied voltage and current to the motor while taking into account all relevant input parameters such as offset and localization. As you can imagine, there are little to no drives available that can drive our specialized and one-of-a-kind motor in an efficient way while still ensuring full control over the output signals. That's why we have decided to develop our own custom motor drives. The result is 2 individual motor drives, one for each motor. This setup not only allows for independent control, but it also allows us to precisely manipulate the electrical currents flowing through each motor, allowing lateral steering of the pod. Lateral steering with motors is challenging, since it requires precisely adjusting these electrical signals to balance the forces acting on the pod. If we now carefully tune these currents, we can create a subtle, yet powerful steering effect, aiding our EMS in keeping the pod perfectly centered in the track at all times. These motor drives are capable of 300 kilowatts of output power. To put that in perspective, the possible output power of these motor drives is 300 kilowatts, way more than we currently need. But this makes sure that our design is future-proof. To put that in perspective, the possible combined output power, 600 kilowatts, is equal to the output power of a Formula 1 car. All of the previously mentioned subsystems require power to operate. And to provide this power, we use a custom-made lithium-ion battery pack. This lithium-ion battery pack consists of 462 individual lithium-ion cells, similar to those found in an electric vehicle. If a fault occurs with one of these cells, the connection can break like a fuse, preventing further damage to the rest of the system. In addition, we have designed and implemented a custom battery management system. This custom battery management system has been optimized for our battery. This is to ensure optimal performance and safety at all times. If you combine this battery management system together with all of these cells, we obtain a battery pack of 600 volts with a peak output power of 150 kilowatts. Batteries, motors, and other electronics all create a significant amount of heat. But cooling them becomes a problem. Why is that? On a hot day, a cool breeze or airflow from a fan helps to regulate your body temperature by carrying away heat. Most electronics rely on a similar principle, using air-cooled systems with fans to dissipate the heat. But in a near vacuum, there is no air to dissipate the heat to, making traditional cooling systems ineffective. To overcome this challenge, we use an advanced thermal management system, and at its core is a large water cooling loop. This water cooling loop extracts the heat from all the components, such as the motors and levitation systems, and collects it to a central point. From here, we would transfer it to the infrastructure using an evaporative-based cooling system. To achieve optimal performance in our pod, we rely on a lot of precise sensor measurements. Take localization, for example. We must know our exact position along the track relative to the steel teeth present on the infrastructure to precisely control the magnets in our motor. This is done using a system that uses a laser to scan a pattern that is present on the infrastructure that resembles a barcode. And after processing this data, we can obtain our position down to an accuracy of 0.1 millimeters. To put that in perspective, this is like you knowing your exact distance to this stage to within the precision of the thickness of a single sheet of paper. Beyond localization, we rely on a wide range of sensors, including voltage, current, pressure, temperature, as well as many other, that track key system parameters in real time. All of these sensors generate a lot of data. In fact, the constant flow of data is enough to watch multiple 4K movies while having a Zoom call. Processing all this data requires 16 custom-designed PCBs, each responsible for processing, gathering, or transmitting data. To ensure seamless communications between them, we rely on multiple industry standard protocols. For example, a CAN bus throughout the pod makes sure that we have reliable and fast communication while keeping the amount of cabling to a minimum. This data is not only used to operate the subsystems. It also allows an engineer to monitor the pod's performance in real time. This is done using a wireless communication link to the ground station. And from here, an engineer can operate the pod while storing all the relevant sensor data. This sensor data can then be further analyzed, helping us improve our system with every single test we perform. In the rare case of an emergency, we need to be able to come to a stop safely, even at high velocities. This is where our pneumatically activated braking system comes into play. In fact, we use two separate braking systems for redundancy reasons. If one of the systems fails, we always have a backup system. These brakes are designed in such a way that you actively need to retract the brakes. This means that we use pressurized air to compress a set of mechanical springs. And in the case we lose power or pressure in the system, this air will escape, extending these mechanical springs and thus automatically deploying our brakes. Infrastructure is also an important part of a Hyperloop system. The infrastructure needs to be as passive as possible. This means that we move a lot of the complex components, such as levitation systems and motors, to the pod itself, dramatically reducing the cost for the infrastructure. While competing in July using the European Hyperloop Center's infrastructure, we still need to be able to test our systems here, in Delft. That's why we have designed a simplified version of the European Hyperloop Center's infrastructure, and we will construct it here in Delft. However, building such a large structure is challenging. To overcome this challenge, we will construct the track ourselves at an external location in just 3 weeks of time. And despite this tight deadline, we will ensure millimeter precision over the entire 50 meters of length. Once the assembly has finished, we will transport the track to Delft, to the Dream Hall. And here, we will lower it onto its anchors using a large crane, while still ensuring the millimeter precision. A remarkable feat for a student team. To summarize, with THEIA, we have introduced many milestones and innovations, including a new motor, full vacuum compatibility, and custom motor drives. These advancements, along with many others, push the boundaries of what is possible in high-speed transportation and bringing the Hyperloop concept into reality. Now, I would like to give the word back to Sophie for some final closing remarks.
Yes, thank you, Daniel, for explaining our incredible design, THEIA. The design that will allow us to demonstrate a fully upskilled, integrated Hyperloop system at the European Hyperloop Center. And with that demonstration, we'll hopefully bring home the prize of the European Hyperloop Week. But luckily, we are not alone in this journey, because none of this would be possible without the help of our dear, dear partners. They are the backbone that allows us to bring the Hyperloop vision to a higher velocity. And you guys support us in so many ways, whether it's material support, financial support, or knowledge and expertise. Each and every one of you has decided to foster innovation and join Delft Hyperloop in its journey towards a better tomorrow. We are extremely grateful for this opportunity, and I would like to take this moment to formally thank you. And then, to my dear, dear team, I want to express my extreme admiration for the milestones that we have reached together. Each and every one of us has grown so much since the beginning of the year as an individual, but that is not in the slightest comparable to how much we've grown towards each other as a team. The Hyperloop industry is facing challenges as we speak, but together with you, I am 100% confident to take them on. Now, this presentation is going to be finished in 2 minutes. And before you guys go and see your, I'm sure, proud families, I want to invite you guys up on the stage for one team photo to memorize this milestone and also to receive the applause that you deserve for your Hyperloop design. And then lastly, to everyone that decided to join us in the Nieuwe Kerk today. A world with the Hyperloop system is getting closer. Every day, we're setting steps towards the realization of the Hyperloop system. But tonight, we took a leap with our vacuum-compatible and upskilled Hyperloop design. We want to invite you on the journey of Delft Hyperloop, because only together we can bring vision to velocity. Thank you.